So, what is this question all about? We have just looked at a situation whereby we are rotating a mass tied to a piece of thread in a vertical circle and in a horizontal circle, and we have seen that tension changes. Now, what are some of the applications of this situation? Now, with me, I have a small bucket. We fill it with water, and then we rotate it in a vertical circle, and then see whether the water pours out at the maximum point of the circle. In other words, we are going to fill it with water and rotate it in that circle like that. You will agree with me that if you put water here, and this is the center of the circular path, so you're going to rotate the bucket like that, like that, like that. You will agree with me that as soon as the bucket maybe reaches some point there, or even there, or even here, the water will start to pour out of that bucket. But we know, or we have been told, that if you were to swing this bucket in that vertical circle like that, let me swing it in this circle so that you can be able to see it properly. If you were to swing that bucket in that vertical circle like that, the water will not pour out. That is what we have been told. But have you ever tried it? So, can we go right ahead and fill this with water and then rotate it? Of course, you will say yes. But I will tell you no. Not at this particular point, because I'll tell you a story. There are those people who like to go to space to go and investigate how space looks like. But they run the danger of things which they do not know. For example, there isn't any atmosphere over there. We don't have any oxygen. And if something happens with the suit which they are wearing, maybe there is a hole or something, they will run out of oxygen, and this one can be very dangerous and they can die. Another thing would be they are not used to be in places where the acceleration due to gravity is zero. That is, in deep space. What would happen to the functioning of the internal body organs? So there are those who like to go there to investigate how our space looks like. But they run the risk and they endanger their lives. Then there is somebody else who likes to get a telescope and views space from a position of complete safety. The astronomer. They remain here on Earth. All they have is telescopes, and they are able to view space from a position of complete safety. At this particular point, I want to be the second person, the astronomer. Reason being, I don't know what might happen if I put water here, rotate it, and maybe something goes wrong and the water pours out on my workstation. I can end up maybe spoiling a pretty expensive machine over here, and that experiment will not be worth the risk. But I'd like you to try. I'd like you to get a plastic container, just a simple plastic container like this, make some holes at the sides, tie a piece of thread, and then hold it at the center, put some water, and then rotate it, and see whether the water will pour out or not. Now, in this lesson, we want to investigate what are the conditions that must be fulfilled for the water not to pour out when the bucket is at the topmost point here. What conditions must be fulfilled? Now, why do we bother to study something like that? We will understand things like looping the loop. You've seen the military planes, especially during parades. Sometimes the plane would go like that and then take a complete, curve. It's referred to as looping the loop. They'll make a complete cycle and come and fly flat, straight. Pretty risky, but they're skills which they have to learn. Now, when the plane is upside down, we are going to look at the conditions that must be fulfilled for the pilot not to fall off the seat, just like the water does not pour out of this bucket. And then finally, we are going to understand the idea of the Hamburg Bridge. What is the Hamburg Bridge? If you look at our highways, you will be able to see some bumps that are very long, and usually vehicles don't slow down along such bridges. They're called Hamburg Bridges. Now, what conditions must be fulfilled for the vehicle not to fly off the road when it is at the topmost part of the Hamburg Bridge? Again, we are going to investigate that in this particular lecture. So take your seat, arm yourself with pen and paper, because I'd like you to do some writing as we go along. And at the same time, if you find that there are some things that I'm mentioning in this video that you can't be able to follow, remember that this will be the fourth part of the overview of uniform circular motion. So if you've not watched the last 3 videos, just hurry up, watch them, and then you'll be able to catch up with the concepts that we are going to talk about in this lecture. However, when I come across a concept that I've already talked about, I will briefly go through it and you'll be able to catch up. So don't worry, let's move over to my blue board and investigate the conditions that must be fulfilled for water not to pour out of the bucket when you're whirling it round in a vertical circle. Of course, don't forget to do it practically now that you're at home. So let us address this situation using a question. And the question reads as follows. A bucket of water is whirled round in a vertical circle. Determine the condition that must be fulfilled for water not to pour out when the bucket is at the highest point of the circle. That is at this particular point. Of course, I want to study the first condition, which is when it is at position A, before I come to position B. Now, the object that we are concerned with, which is moving in this particular circle, is water in the bucket. So when I talk about the mass of the object, it is the mass of the water in the bucket. Let's look at the 2 forces which are acting on this mass. One of them is that the earth is pulling that water downwards with a force which is equal to the weight of the water. So one of the forces is the weight of the water. What is the other force? The other force is that the bottom of the bucket is applying a force called a reaction force on it, R, because we know the bottom part of the bucket, if it was not there, the water would just pour out. So the bottom part of the bucket must be applying an upward force on the water. Remember, we have forgotten about the tension in this particular string here. It is conveyed to the water all the way to the side of the bucket, and now it is the bottom of the bucket which is applying that force. These are the 2 forces which are acting on the water at this particular point. And so is the water in any one container on a horizontal surface. There will be 2 forces. One of them is the weight of the water. The other one is the force exerted by the container from the bottom vertically upwards. Now let us think about, so in this particular situation, the force which is providing the centripetal force when the bucket is at position A is, of course, we start with our popular equation. A resultant force on the water is going to be equal to ma. Remember, the acceleration of the water is towards the center of the circular path, and of course the resultant force is R minus mg is equals to ma. And we know that our A is v squared over r. So why don't we make r to be the subject of this equation? So we have ma plus mg. And of course, this one gives us this relationship here. M v squared over r plus mg. I'm just going through some of the points we talked about when we were talking about vertical circle as far as a stone tied to a piece of thread is concerned. Let us look at the bucket when it is in position B. As usual, we want to ask ourselves, what are the forces acting? Again, the first force is the weight of the water, vertically downwards, mg. The second force is, of course, the reaction from the bottom of the bucket, again vertically downwards, like that. The reason why I started with this situation here is for you to see that R and mg are in opposite direction. Over here, R and mg are in the same direction. And remember, it is position B where the water can easily fall out or pour out. So at that point, again, when we use the equation, resultant force is equals to MA. Now I know you're getting used to using this equation here. What would be the resultant force given that the two forces R and mg are acting towards the center of the circular path? Of course, I know you have said the resultant force is R plus mg is equals to MA. Again, we make R to be the subject of this expression. We are going to have MA minus mg. When I substitute the A with V squared over R, I get this expression here. R is equal to mv squared over R minus mg. Remember, this is a centripetal force. And remember also, it is a resultant force. Now, for the water not to pour out, the value of R must be greater than or equal to 0. It must be greater than 0 or just equal to 0. That is the condition that must be fulfilled. So, this R, which is equal to mv squared over R minus mg, I'm substituting R with this value and I'm saying R is greater than or equal to 0. So I forget the value of R. Now I'm going to deal with this expression here because mv squared over R minus mg represents R, which must be greater than or equal to 0. Of course, I can take mg to the other side of the equal sign, and I have this. mv squared over R must be greater than or equal to 0. It is at this point that we get the first condition. Actually, at this point, I should have written mg, because I've just taken minus mg to the other side of this inequality, and now I'm in a position to state the first condition, that the centripetal force, F centripetal, must be greater than or equal to the weight of water in the bucket. I can go ahead and cancel out the m's. If I cancel out this m and I cancel this m, I come up with this. V squared over R must be greater than or equal to the acceleration due to gravity. So I can also state that condition by saying the centripetal acceleration must be greater than or equal to the value of the acceleration due to gravity. And remember, acceleration due to gravity of the Earth is 10 meters per second squared. So this further implies that I can be able to say that the centripetal acceleration, A centripetal, is greater than or equal to 10 meters per second squared, because I know its value. And finally, I can go ahead and make V to be the subject of the expression, because I want to know what about the speed. And for me to do that, I can multiply both sides by R. So first of all, I'm going to get V squared is greater than or equal to RG, after multiplying by R. And then I make V to be the subject, and by doing square root both sides, and this is what I get. So the speed with which I must rotate this bucket with, especially at this point, must be greater than or equal to the square root of RG. What is R? R is the radius of the circular path. G is the acceleration due to gravity. And you can see from this expression, the condition is independent of the mass of the object which is inside here. So it does not matter about the mass of the water inside there. That speed is dependent on the radius and the value of G. So given that G is some kind of constant, because over here I can be able to get the square root of 10, I'll get 3 point a few values there. I can be able to say that V is greater than or equal to 3 point the number of values I have there. Maybe let us say, just for instance, let us say 3.16. Actually, the square root of 10 is 3.16 multiplied by the square root of the radius. You can also state that condition that way. But up to this point, you can state that condition in terms of the weight of the water in the bucket. The centripetal force must be greater than or equal to the weight of the water in the bucket. Or you can say that the centripetal acceleration must be greater than the acceleration due to gravity. Or you can even write down this condition here. And that is the condition which must be fulfilled for water not to pour out of the bucket. So in question 12, we have the Hamburg Bridge would be, a situation like this. That is the Hamburg Bridge. Of course, the car is somewhere around here. These are the tires of the car. So there we have a beautiful car over there. And it's moving over this Hamburg Bridge. Of course, here it is usually a bit smoother. It's usually not very, very sharp. That is where you find that drivers are able to move over the Hamburg Bridge very easily, because it doesn't have sharp angles. It's very smooth over here. But if the driver is not careful, this car can fly off this bridge and there will be no contact between the tires and the road. If there is any kind of change in direction, then it can cause an accident. Let's look at some of the forces which are acting on the car at this particular point. One of them is the weight of the car vertically downwards. Of course, we are talking about the forces which are acting on M, the mass, which is moving in this particular circular path. And remember, this Hamburg Bridge is such that it is constructed. The engineers determined the size of the Hamburg Bridge by measuring some sort of radius from some point there. So this is the radius of that arc of the bridge. The other force, of course, that is acting on the car is one due to the contact between the car and the road, the normal reaction, so to speak. But more accurately put, it is the normal component of the contact force. So those are the two forces which are acting on the car. Remember, when it is at this particular point, it is moving in a circular path, and definitely it is accelerating towards the center of the circular path. There is a resultant force towards the center of the circular path. So we can start our expression by saying that resultant force towards the center of the circular path is equals to ma. That resultant force is given by mg minus r is equals to m. And at this point, I just want to replace the a with v squared over r, so that I can reduce the number of steps that I have here. And here I can move r to the other side, which means I'm going to have mg minus mv squared over r is going to be equal to r. Let me rearrange this by starting with r is equal to mg minus mv squared over r. Now the condition which we must observe here is that the value of r must at least have a value. It must be greater than or equal to 0. It must have a value for the car not to fly off that bridge. So what does that mean? If I go back to this expression here, and they say that mg minus mv squared over r is equal to r, where r is the r that we are talking about here, we can say that since r is greater than that, I'm going to substitute this value of r with this expression here. This expression is the one which will come and take the place of this r. So I'm going to write mg minus mv squared over r. Remember, this is the weight of the car. This is the centripetal force. And then I bring in this inequality here, like that. And now I can say that mg is greater than or equal to. I bring the centripetal force to the other side of the equal sign. And this is what I have. And at this point, I can be able to state my first condition, that the weight of the car, weight of car, must be greater than, or equal to centripetal force, F centripetal. That is the first condition. Of course, I can develop the other condition by saying that the centripetal force must be less than the weight of the car. I can also say something like that. F centripetal, which is this one, must be less than or equal to the weight of the car. We have access to the centripetal force. We can do something about it, but there's nothing we can do about the weight of the car. So we can state this by saying the amount of centripetal force which the car has must be less than the weight of that particular car. Meaning that since we know the speed at which the car is moving, in other words, mv squared over r is less than or equal to mg, Let's go ahead and cancel out the m's so that we remain with v squared over r, which is less than or equal to g, and we can say that the acceleration centripetal acceleration must be less than the acceleration due to gravity. But I want to center around the speed of the car, because it is the speed of the car that most people would want to understand. What about the speed of the car? So in order to get the speed of the car, I'm going to make v to be the subject, and find that that one must be less than or equal to the square root of rg. The speed of the car must be less than or just equal to the square root of rg, where r is the radius of this particular arc. And this is where the speed limit comes in. Speed limit. At such a bridge, you will definitely see a sign showing the speed limit. So, irrespective of the mass of the car, whether it is a truck or a small van, that speed must not be exceeded. The speed must be less than that speed which is shown on that signboard. This is the condition which most people would understand. The speed of the car, because they have access to the speedometer. They can look at the speedometer and be able to say, okay, I'm not supposed to exceed that speed. If I exceed that speed, then this car is likely to fly off the Hamburg Bridge. Now, when we compare this with the speed over here, we saw that the speed with which the bucket must swing, or the speed with which the plane must move, must be greater than or equal to the square root of rg. Here it is the other way around, that for the Hamburg Bridge, the speed of the car must be less than or equal to the square root of rg. And that is how you would come up with these conditions.